Hello friends, welcome back to my YouTube channel Journey with Vijay Kumar Shrivastav. Today I am going to present the topic Basics of Soil. Before presentation I would like to introduce myself. I am Vijay Kumar Shrivastav. I have done M.Sc Agriculture with specialization in Agronomy from Pant University of Agriculture and Technology Pantnagar in 1996. Hope this presentation will be very useful to all of you. So let's proceed to the presentation. First we will study about soil structure. Soil structure is the arrangement and organization of soil particles into natural units of aggregation. Except for sand, soil particles do not exist singularly in soil but rather are arranged into aggregates or group of particles. Soil aggregates are formed both by physical forces and by binding agents, which are principally products of decomposition of organic matter. Aggregates formed by binding agents are more stable and able to resist the destructive force of water and cultivation. Aggregates formed by physical forces such as wetting and drying cycles as well as freezing and thawing are relatively unstable and are subject to quicker decomposition. Soil aggregation normally occurs when ample organic matter is present. Aggregation sharply increases with increase in soil carbon content from 0 to 2% or more. However, soil aggregation can also be easily destroyed by flooding or by compaction or working the soil when it is too wet. Soil structure has an important influence on plant growth, primarily as it affects moisture relationship, aeration, heat transfer, and mechanical impedance of root growth. For example, good seedbed preparation is directly related to moisture and heat transfer. A fine granular structure is ideal in this respect. The movement of water and air through the soil is dependent on porosity, which is highly influenced by structure. Good granular structure provides adequate porosity for moisture infiltration and air exchange. However, where surface crusting or subsurface clay pans or hard pans exist, plant growth is hindered because of restricted porosity. There are in general four primary types of structure based upon shapes and arrangement of aggregates. First one is granular structure, second is blocky structure, third is columnar or prismatic, and fourth is platy structure. This also includes two additional aggregates, massive and aggregated granular, which are considered to be structureless. The most favorable water relationship occurs with soil that are columnar, blocky or aggregated granular structure. Platy structure in fine and medium soils will impede downwards movement of water. First type of soil structure is granular structure. All round aggregates may be placed in this category, not exceeding an inch in diameter. These rounded complexes usually loosely arranged and readily separated. When wetted, the intervening spaces generally are not closed so readily by swelling as may be the case with a blocky structure condition. Therefore, in sphere-like structure, infiltration, percolation and aeration are not affected by wetting of soils. The aggregates of these groups are mainly termed as granular, which are relatively less porous. When the granulars are very porous, it is termed as a crumb. This is specific to surface soil, particularly high in organic matter and grassland soils. Second soil structure is plate-like platy structure. In this type, the aggregates are arranged in relatively thin horizontal plates or leaflets. The horizontal axis or dimensions are larger than the vertical axis. When the units and layers are thick, they are called platy. When they are thin, then it is called laminar. Platy structure is most noticeable in the surface layers of virgin soils but may be present in the subsoil. This type is inherited from the parent material, especially by the action of water or ice. Third soil structure is prism-like or columnar. The vertical axis is more developed than horizontal, giving a pillar-like shape. Vary in length from 1 to 10 centimeters. Commonly occur in subsoil horizons of arid and semi-arid regions. When the tops are rounded, the structure is termed as columnar. When the tops are flat or plain, level and clear cut, it is called as prismatic. Fourth soil structure is blocky. All three dimensions are about the same size. The aggregates have been reduced to blocks, irregularly six-faced with their three dimensions more or less equal. When the faces are flat and distinct and the edges are sharp angular, the structure is named as angular blocky. When the faces and edges are mainly rounded, it is called subangular blocky. These types usually are confined to the subsoil and characteristics have much to do with the soil drainage, aeration and root penetration. Soil structure can be improved with proper cultural practices, reducing tillage, improving internal drainage, cover crops cultivation, liming or adding sulfur to the soil, using grasses or deep-rooted crops in rotation, incorporating crop residue and adding organic material or soil amendments. A structure can easily be destroyed by heavy tillage equipment or excess operations. Now to study soil texture. Soil texture refers to the relative proportion of particles, or it is the relative percentage by weight of the three soil separates, sand, silt and clay, or simply refers to the size of soil particles. The proportion of each size group in a given soil cannot be easily altered, and it is the basic property of a soil. The soil separates are defined in terms of diameter in millimeters of the particles. Particles less than 2 mm is called fine earth, normally considered in chemical and mechanical analysis. The components of fine earth are sand, silt and clay, which are known as soil separates. The size limits of sand, silt and clay have been established by various organizations. There are a number of systems of naming soil separates in case of soil texture. As per USDA classification, United States Department of Agriculture classification, it has been categorized in 7 groups. First one is clay, having diameter less than 0.002 millimeters, silt having diameter of 0.002 to 0.05 millimeters, very fine sand 0.05 to 0.1 millimeter, fine sand having 0.1 to 0.25 millimeters, medium sand 0.25 to 0.5 millimeters, coarse sand having diameter of 0.5 to 1 millimeter, and very coarse sand having diameter 1 to 2 millimeter. There is textural triangle to analyze the texture classes of the soil. It is used to determine the soil textural name after the percentage of sand, silt and clay are determined from a laboratory analysis. Since the soil textural classification includes only mineral particles and those of less than 2 mm diameter, the sand plus silt plus clay percentage equal 100%. Knowing the amount of any two fractions automatically fixes the percentage of the third one. The principal classes pertaining to the texture are sand, loamy sand, sandy loam, silt loam, clay loam, silt clay loam and clay soils in increasing order of their content of fine separates. Particles larger than 2 mm are considered rock fragments, and those that are less than 2 mm are considered fine earth fraction. Here we have shown the textural triangle. To using the diagram, we have to locate the percentage of clay first and project inward parallel to sand line. Do likewise for the percent silt and project inward parallel to clay line, and for sand project inward parallel to silt line. The point at which the projections cross or intersect will identify the class name. Sometimes the intersecting point exactly fall on the line between the textural classes. Then it is customary to use the name of the finer fraction when it happens. Like soil containing 40% clay and 30% sand will have automatically 30% silt. A textural class description of a soil reveals a lot about soil-plant interactions, since the physical properties of soils are determined largely by texture. In mineral soils, the exchange capacity, means ability to hold plant nutrient elements, is related closely to the amount and kind of clay in the soil. The water holding capacity is determined largely by the particle size distribution. The fine textured soils, which are high in silt and clay, hold more water than coarse textured soils, which are sandy soils. Water percolates more quickly and more deeply into light soils, but heavier soils have the greater water holding capacity per cubic foot. Fine textured soils are also more compact, have slower movement of water and air, and it can be more difficult to till. Soil texture has an important influence upon crop production. From the standpoint of plant growth, medium textured soils such as loams, sandy loams, and silt loams are probably the most ideal soil for cultivation. Now to study about soil porosity. Soil porosity refers to that part of a soil volume that is not occupied by soil particles or organic matter. The pore space of a soil is the space occupied by air and water. The amount or ratio of pore space in a soil is determined by the arrangement of soil particles like sand, silt and clay. In sandy soils, the particles are arranged closely and the pore space is low. In clay soils, the particles are arranged in porous aggregates and the pore space is high. Presence of organic matter increases the pore space. As a formula, porosity is defined as pore space per cubic centimeter divided by soil volume per cubic centimeter multiplied by 100. In case of sandy surface soil, the porosity is 35 to 50%. Medium to fine texture soil, it is 50 to 60%. And in case of compact subsoil, it is around 25 to 30%. On the basis of pores, size of pores, it is categorized in two types. First one is macropores, which are also known as non-capillary pores, where the diameter is more than 0.05 millimeters, and second is micropores, which are known as capillary pores, where the pore space diameter is less than 0.05 millimeter. In macropores, air and water moves freely due to gravitation and mass flow. In micropores, the movement of air and water is very slow and restricted to capillary movement and diffusion. Sandy soil have more macropores and clay soils have more micropores. So in sandy soils, water and air movement is rapid due to macropores through the pore space is higher, and in clay soils, the air and water is slower due to micropores through the total pore space is higher. Loamy soils will have 50% porosity and have equal portion of macro and micropores. Here to study the significance and manipulation of soil porosity, the bulk density and pore space are interrelated. Development of low bulk density values also means the development of large amount of pore spaces. In nature, low bulk density values are usually found in soils with high organic matter contents. High biological activities are necessary for formation and large accumulation of organic matter. Together with the effect of soil organisms, the high humus content will encourage aggregation, increasing in this way soil porosity and thereby decreasing bulk density values. The cultivation effect of the soil micro and microfauna produces an intricate system of macropores, which is a major factor for lowering the bulk density of soil. Continuous cropping is noted to decrease the amount of organic matter in soils and is expected to decrease soil aggregation. Tillage by plowing is designed to increase the pore space in soils, but is in fact decreasing soil organic matter. To alleviate these problems, conservation tillage and no tillage have been introduced. Though many claims that this increase the organic matter, the latter have not always increased the total pore space. Now we will study about particle density. The weight per unit volume of the solid portion of soil is called particle density. Generally, particle density of normal soil is 2.65 gram per cubic centimeter. The particle density is higher if large amount of heavy minerals such as magnetite, limonite and hematite are present in the soil. With increase in organic matter of the soil, the particle density decreases. Particle density is also termed as true density. Now to study bulk density. The oven dry weight of a unit volume of soil inclusive of porous spaces is called bulk density. Units are expressed as the weight at oven dry and volume at field capacity water content, expressed as grams per cubic centimeter or pounds per cubic foot. Bulk density is used to convert water measurements from a weight basis to a volume basis. The bulk density of a soil is always smaller than its particle density. Bulk density normally decreases as mineral soils becomes finer in texture. The bulk density varies indirectly with the total porous space present in the soil and gives a good estimate of the porosity of the soil. Bulk density is of greater importance than particle density in understanding the physical behavior of the soil. Generally, soils with low bulk densities have favorable physical conditions. Other factors affecting soil bulk density includes freeze or thaw process, plant root growth and decay, wormholes and organic matter present in the soil. Here to study soil tilth. As a simply defined, tilth refers to the physical condition of the soil in its relation to plant growth. Tilth not only depends on granulation and its stability, but also on moisture content, degree of aeration, rate of water infiltration, drainage, and capillary water capacity. Tilth can change often and markedly. For example, working properties of fine texture soils may be altered by a slight change in moisture. One of the objectives of cultivation is to encourage and maintain soil tilth. However, when improperly administered, tillage operations may seriously impair tilth directly or set the stage for later deterioration, especially in the upper furrow slice. Now to study organic matter. Soil organic matter is the organic fraction of the soil. It consists of plant and animal residue in various stages of decomposition, living soil organisms and substances synthesized by these organisms. Practically every soil property is affected by soil organic matter. Organic matter beneficially influence soil structure, soil condition, soil bulk density, soil erosion control, water infiltration, plant growth and root development, permeability, total water holding capacity, biological activity, oxygen availability, nutrient availability, and tilth, as well as many other factors that make the soil a healthy nature resource for plant growth. Soil organic matter plays a key role in biological, physical, and chemical functions in soil. The amount of organic matter that may accumulate in the soil depends upon temperature, moisture, aeration, soil pH, microbial population, and the quantity and chemical makeup of the plant residue returned to the soil. The dark colored organic residue typically found nearer the soil surface is called humus. Humus increases friability of soils, improves tilth, and facilitates aeration and water infiltration in the soil. Soil depth. Soil depth is the dimensions from the soil surface to bedrock, hardpan or water table to a specified soil depth or to a root growth restrictive layer. The depth from the soil surface to bedrock influences the soil's potential for plant growth and agronomic practices. The deeper the soil, the more total soil water storage is available for plant use. The depth of soil to which the roots of a plant can readily penetrate to in order to reach water and nutrients. Minimum of 3 to 5 feet is desirable. Deeper soils are better because they can hold more nutrient and water. A shallow depth to bedrock results in a lower available soil water capacity and thus drier conditions for plants. Equipment induced compaction layers or naturally occurring impervious layer restrict the downward movement of water and root penetration. Here to study about water tables. Water tables can be a barrier for root development because of restricted oxygen supply. Most crops grow best where the water table is greater than 6 feet below the soil surface. Adequate soil drainage must be present for sustained growth of most plants. Additionally, when groundwater is saline, upward movements and its subsequent evaporation at the surface of the soil adds to the salinizing of soils. providing artificial drainage for poorly drained soils and for soils with high concentrations of salt increases the soil depth for potential root development. In other situations where water tables are not a barrier to root development, planned water table control and management of shallow groundwater can supply all or part of the seasonal crop water needs. The water must be high quality, salt free and held at near to a constant elevation. The water table level should be controlled to provide water according to the crop needs. Now we will study about chemical properties of soil. The physical and chemical weathering of materials on the earth's surface forms soil. These materials may have been rock or they may have materials that transported from elsewhere and deposited over rock. Exposure of the surface to water, oxygen, organic matter and carbon dioxide brings about chemical alteration to the material. Oxidation, reduction, hydration, hydrolysis and carbonation contributes to chemical and physical changes in the surface material. If it is rock, the material gradually breaks down into smaller particles, forming a mineral soil. If it is a transported material such as glacial till or sludges, weathering can affect soil chemistry and mineralogy. The chemical and mineralogical composition of the soil varies with respect to depth or horizon. Weathering intensity decreases with depth from the surface. The longer the weathering has proceeded, the thicker the weathered layer and the greater the dissimilarity from the original material. In mineral soils, organic matter content generally decreases with depth. Now we will study about the chemical properties, cation exchange capacity, CEC. Clays and organic matter typically possess net negative charge. Positively charged cations are attracted to these negatively charged particles, just as opposite poles of magnets attract one another. Cation exchange is the ability of soil clays and organic matter to adsorb and exchange cations with those in soil solution. A dynamic equilibrium exists between absorbed cations and those in soil solution. Cation adsorption is reversible if other cations in soil solutions are sufficiently concentrated to displace those attracted to the negative charge on clay and organic matter surfaces. The quantity of cation exchange is measured per unit of soil weight and is termed cation exchange capacity. Organic colloids exhibit much greater cation exchange capacity than clays. Various clays also exhibit different exchange capacities. Thus, cation exchange capacity of soil is dependent upon both organic matter content and types of clays. Cation exchange capacity is an important phenomenon for two reasons. First, exchangeable cations such as calcium, magnesium and potassium are readily available for plant uptake. Cations absorbed to exchange sites are more resistant to leaching or downward movement in soil with water. Movement of cations below the rooting depth of plant is associated with weathering of soils. Greater cation exchange capacity helps decrease these losses. Pesticides or organic with positively charged function groups are also attracted to cation exchange sites and may be removed from the soil solution, making them less subject to loss and potential pollution. Calcium is normally the predominant exchangeable cations in soil, even in acid weathered soils. In highly weathered soils, aluminum may become the dominant exchangeable cation. The cations of calcium, magnesium, potassium and sodium produce an alkaline reaction in water and are termed bases or basic cations. Aluminum and hydrogen ions produce acidity in water and are called acidic cations. The percentage of cation exchange capacity occupied by basic cations is called percent base saturation. The greater the percentage base saturation, the higher the soil pH. Now to study soil pH. Soil pH is a commonly measured soil chemical property and also one of the more informative. Soil pH implies certain characteristics that might be associated with a soil. Since pH, which is the negative log of the hydrogen ion activity in solution, is an inverse or negative function, Soil pH decreases as hydrogen ion or acidity increases in soil solution. Soil pH increases as acidity decreases. A soil pH of 7 is considered neutral. Soil pH value greater than 7 signify alkaline conditions, whereas those with value less than 7 indicate acidic conditions. Soil pH typically ranges from 4 to 8.5, but it can be low as 2 in material associated with pyrite oxidation and acid mine drainage. Soil pH has a profound influence on plant growth. Soil pH affects the quantity, activity and types of microorganisms in soil, which in turn influence decomposition of crop residue, manures, sludges and other organics. It also affects other nutrients transformations and the solubility or plant availability of many plant essential nutrients. Phosphorus, for example, is most available in slightly acid to slightly alkaline soils, while all essential micronutrients except molybdenum become more available with decreasing pH. Aluminum, manganese and even iron can become sufficiently soluble at pH less than 5.5 to become toxic to plants. Bacteria, which are important mediators of numerous nutrient transformation mechanisms in soil, generally tend to be most active in slightly acid to alkaline conditions. Here to study about salt affected soils. Salt affected soils are unique in that they have variations in level of salinity, different kinds of salts, differences in climatic patterns and varying materials. Salts in the soil water solution decreases the amount of water available for plant uptake. Salt affected soils have been internationally classified into general categories, which are three. First one is saline soils, second is sodic soils and third is saline sodic soils. In case of saline soils, the electrical conductivity is more than 4 and sodium absorption ratio is 0 to 13 and pH ranges 8.5 and exchangeable sodium percentage is less than 15. While in case of sodic soils, the electrical conductivity is 4 where the sodium adsorption ratio is more than 13 and pH will range more than 8.5 and exchangeable sodium percentage is more than 15. In case of saline sodic soils, the electrical conductivity will be more than 4, sodium absorption ratio is more than 13, pH will be less than 8.5 and exchangeable sodium percentage less than 15. Salt affected soils are generally classified using electrical conductivity of the soil water extract corrected at 25 degrees centigrade. Units are expressed in decisiemens per meter or millimoles per centimeter. The adverse effects of salts in depressing plants growth are caused by at least one of three factors. First one is direct physical effect of soil in preventing soil water uptake by plant roots because of increased osmotic tension. Second, direct chemical effect of salts in disrupting the nutritional and metabolic process of plants. And third, indirect effect of salts in altering soil structure, permeability and aeration. So this presentation was all about basics of soil. Hope this will be very useful to all of you. Now my presentation ends here. Thank you very much. I have given here my YouTube channel details, Journey with Vijay Kumar Shrivastav. Having request, please visit the channel, subscribe it and provide your kind and valuable feedback for further improvements. Thank you.